Good afternoon, welcome back to the gaseous state class. So, today we'll see some theory regarding the non-ideal behavior of the gases. See, when gases were experimented, whether they are following the ideal gas law, PV equal to nRT or not, Boyle's law, Charles law or whatever it is, interesting facts has come out that most of the gases are not following the ideal gas equations. There are so many deviations. When they plotted PV versus P graph, the ideal gas equation is following the parallel to the x-axis, but whereas here hydrogen and helium, they followed the one type, and carbon monoxide, methane, other gases is followed some other type. Some are positive deviations, some positive negative deviations, then positive deviations, like that it is followed. This finally the conclusion is it is not following the ideal gas equations. For some time only it is following, and again depends upon the nature of the gas, and many other things are also coming in the way. Then started wonderful. I started the why it has failed ideal gas equation, or where it has failed. We have seen some 6 postulates or some postulates. It is random motion, no issue, that is almost okay. And the elastic collisions are there, agreed. And pressure exerted in all directions, yes. Many things are okay, but 2 things are not okay. Those 2 are when pressure is exerted on the wall, only 3 sides molecules are there, 4th side there is no molecule. So though there is no intermolecular forces we are considering, it is not correct in all the time. It is correct only at the low pressures. So the pressure whatever is supposed to exert, it is not. So we are something is shortage. So we have to add something for the real gas. Similarly, in the volume, when we are considered the ideal gas, volume considered to the container, the volume occupied by the gas is negligible, but not so. There is a small volume occupied. So, in the ideal gas, there is a higher volume and the lower pressure. So, there are corrections applied. The ideal gas equation, P actually equal to P plus a n square by v square. A is a constant, n is a number of moles, and the correction of the volume side v equal is v minus nb. Finally, the ideal gas equation equal real gas equation, ideal gas equation P equal to nRT as van der Waals equation converted to P plus a n square by v square into v minus nb equal to nRT. So whereas a and b are constants, n is a number of moles and v is the volume, p is the pressure. So this is for the real gas equation. Here one more term we are introducing as a compressibility factor. What is that? Z equal to Pv by RT. Normally Pv by nRT equal to 1, but that is holds good at low pressures and high temperatures. Otherwise Z may be more for high pressures, Z may be less for intermediate pressures. So that is depends upon the nature of the gas and other things. If you see the one particular up to particular range, temperature is particular temperature range, it is following the nearer to the ideal gas equation. So that is temperature is called a Boyle temperature. Boyle's law, Boyle temperature. That is the gas which is obeying the Boyle's law up to particular temperature, that is a Boyle's temperature. Nice. Here, though Z equal to Pv by nRT, if you see nRT by Pv by nRT, in this P and V real if you take, Z equal to actually V real by V ideal. That is the one more application in this. Now, one more term we are calling as a critical temperature. Most of the time people got the confusion about the critical temperature. Say, if you see the carbon dioxide isotherms, there one thing is, new thing is revealed, that at particular temperature, beyond the particular temperature, even if you are applying whatever may be the pressure, gas cannot be liquefied. But if you see most of the gases we can liquefy at particular temperature, applying by temperatures and lowering the temperatures. If you see the carbon dioxide at 50 degrees centigrade is fully isotherm and it is meeting all the gases laws. Up to 31, okay. So below that, at 73 bar, it is liquefied. That temperature is, that means at particular temperature, beyond the particular temperature, there will not be any liquid existence, and whatever may be the pressure application, it cannot be liquefied. That temperature is critical temperature. At the critical temperature, whatever the volume is critical volume, and whatever the pressure is critical pressure. The other two are only related with the temperature. Critical temperature is a 1. Below that, by applying pressure, you can liquefy the gases. For example, everybody knows about the water. Water 100 degrees centigrade, 1 atmosphere, it is a boiling. But it is not the critical temperature. 6 atmospheres, it is 150 degrees centigrade boiling. Like that, if it is going on, 220 kg up to, also even if you can put the pressure, that is around some 320 temperature and all. That is the critical temperature of the water. That means above that, you cannot liquefy the water. That means there is a temperature, beyond that, below that it will be liquid by applying the other conditions. Above that, it cannot be a liquid at all, whatever may be the conditions. That is the liquid, critical temperatures. We can see the carbon dioxide isotherms tomorrow, but most point of view is the critical temperature, and similarly boiling point. Boiling point is whenever the vapor pressure of the any liquid is equal to the atmospheric pressure. At that temperature it will boil. Atmospheric pressure, normally we will take it as 1 atm, and particularly for the oil, for the water, if you see, at 100 degrees centigrade, the vapor pressure of the water is equivalent to the atmospheric pressure. That is called the boiling point at 100 degrees centigrade. 99.6 also, the small correction because of this one. So, any liquid that will all the time gives the some vapor pressure, depends upon the temperature, depends upon the nature of the liquid. So, that is about the boiling point. And from the extension of the gas state, normally we will go to the liquid states. Means by condensing, that means by lowering the temperature, by applying more pressure, the liquids will, the gases will come to the liquids. So by applying pressure on the, means volume reduction will not be there much on the liquids. So shape changes will be there, depends upon the containers and all. So volume correction will not be much by applying pressure. So it is an extension of the gas state. So we'll see the liquids tomorrow. Not much is there, some small things are there. Thank you very much.